Hello everyone from Math 2000, Linear Algebra. It's Professor Winson here again with a video on your ZyBooks Section 5.3 titled Linear Independence and Linear Dependence, or just Dependence. Okay. So I'm just going to read this first sentence of the section summary because this is the important part, what the section is about. This section looks at whether a vector in a set is a linear combination of some of the other vectors in that same set. Okay. I'm going to read the rest of that, and you got the objectives here. Alright, so the first part of this is, and there's some definitions here on the linear independence of a set of vectors, or the dependence of a set of vectors. Alright, so a set S containing vectors v1, v2, all the way up to vector n of vectors in Rm, say, right? So say all these vectors have m components. A set of n vectors is linearly independent if the only solution to this equation, a1 v1 plus a2 v2 plus all the way up to an vn equals the zero vector, if the only solution to this equation is the trivial solution, right? So where the values of a1 through an are all 0. Right, because remember this is, if I set this equation up here, this a1 v1 plus a2 v2 and so on equal to the 0 vector, this is going to give me a homogeneous system where a1, a2, and an, those are the unknowns. And remember, every homogeneous system has at least the trivial solution, right, where all the values of the unknowns are 0. Now, if that's not the only solution, then they say that this set of vectors is linearly dependent. Right? A set of vectors is linearly dependent if it's not linearly independent, right? So if this equation, this system that we set up, this homogeneous system, if it has more than just the 0 solution, if it has more than just the trivial solution, then the set of vectors involved is said to be linearly dependent. And we'll see later that when a set of vectors is linearly dependent, that means that at least one of the vectors in this set can be written as a linear combination of other vectors in the set. Whereas when a set of vectors is linearly independent, none of the vectors in the set can be written as a linear combination of other vectors in the set. They're all independent of one another. They can't be written as a linear combination of other vectors. They don't depend on other vectors. Alright, so I'll do one of these first as an example, and I'm sure we'll get to others later too. So it says here in this example, determine whether each set of vectors is linearly independent or linearly dependent. Alright, so this part A, we're given the set of vectors, v1 is 1, 0, negative 2, v2 is 0, 2, 1, and v3 is negative 1, 2, 3. Right, so I'm going to write this out and go to a piece of paper, and we'll determine if this set of these three vectors are independent or dependent. Okay, so here's this set of three vectors, and again we're asked, are these three vectors linearly independent or linearly dependent? So again, they're called v1, v2, and v3 on the example. So in order to determine independence or dependence, remember, we're going to look at this equation. take a linear combination of the vectors. Right, so some number a1 times v1 plus some number a2 times v2 plus some number a3 times v3, and then ask yourself, is there a linear combination? We're going to try to find a1, a2, and a3 that make the 0 vector. Now here, these are all vectors with 3 components, so the 0 vector here is, with 3 zeros. Now, again, the trivial solution is always a solution to a homogeneous system like this. Remember we have zeros all on the other side of the equal sign. So does this equation have solutions other than the trivial solution? That's the big question. Right? Does this equation have solutions, values of a1, a2, and a3 other than the trivial solution? And again, the trivial solution is where the values of those unknowns, a1, a2, and a3 are all 0. Because again, that's an obvious solution, right? A trivial solution. If I replace a1, a2, and a3 with 0, you'd have 0 plus 0 plus 0. You'd get the 0 vector plus the 0 vector plus the 0 vector equals the 0 vector. It's obvious. Now, the answer to this question, if the answer to this question is no, then the vectors are independent, right? So if no, if not, if there aren't any other solutions besides the trivial solution, the vectors are linearly independent, or I'll just say independent. And if there are, if yes, if the answer to this question is yes, if there are other solutions besides the trivial solution, then the vectors are dependent. And I'll show you that, you can, if there are other solutions besides the trivial solution, then you can show that, at least one of these vectors can be expressed as a linear combination of the other two, or at least one of the other vectors, right? So one of these vectors depends on the other ones, right? Maybe some of the other ones. So the vectors are dependent. All right, now you've already seen me write linear combinations as systems in section 5.2. So if we look at that equation here, a1 v1 plus a2 v2 plus a3 v3, we're going to be this will be the augmented matrix for that system. Down the first column will be the coefficients of a1, but the coefficients of a1 are just going to be the components of vector 1, right, v1 there. So down the first column, 1, 0, -2. Down the second column will be the coefficients of a2, which will be just the components of vector v2, so 0, 2, 1. Down the third column, the coefficients of a3, which will be just the components of vector v3. Then the equal sign, the bar, and then the other side, just a bunch of zeros. Right? It's a homogeneous system. You get the 0 vector on the other side. And really, very often I'm going to ignore this, because if you have a column of zeros and then you go through and do elementary row operations to put this matrix into echelon form or reduced echelon form, this column of zeros is going to remain a column of zeros, right? It will not change at all. The only thing that's going to change is the coefficient matrix side, right, the left side. But I'll write the zeros in for now. Later on we can ignore them, just imagine that they're there. Alright, so I'm going to go to the calculator and put this into reduced row echelon form in it, and hopefully you know how to enter a matrix by now in your calculator and put it in reduced row echelon form. So I'm just going to pull a calculator up and come back when that's done. Okay, so you see on my calculator there now, again, I ignored the column of zeros because, like I said earlier, this column of zeros is going to stay a column of zeros, and I only entered the coefficient matrix, so that's why it's a 3 by 3 on my calculator and not a 3 by 4. So this into row reduced echelon form is, first row 1 0 negative 1 and 0. Second row 0 1 1 and 0, and the third row is all zeros 0 0 0 0. So in this particular system, so now we're looking at this reduced echelon form of the matrix. There is a free variable. See how this third column here is not, there's a pivot in the first column, a pivot in the second column. There's no pivot in the third column. So the value of A3, right, that we're looking for A1, A2, and A3 here, right, in this equation. The value of A3 is free. And remember what that means about the system. That means, the system has more than just the trivial solution, right? That means that this system has infinitely many solutions. And if you look, even if you look at the last row, we're still okay, because the last row just says 0 equals 0. All right, this last row here just says 0 equals 0, which is fine. 0 is equal to 0. That is a true statement. So you can ignore that and work with the top two rows. All right, so let's work with the top two rows. So remember this. So this second row here tells me that A1, or sorry, A2. This is in the second column. 1A2, A2 plus A3 equals 0. So A2 must equal the opposite of A3, right? If I subtract A3 from both sides. And then from this first row, A1 minus A3 must be equal to 0. Then I add A3, solve for A1. The value of A1 will be equal to A3. And again, A3 is whatever I want. Right? So here's an example of a non-trivial solution to this system. I just replace pick anything I want for A3. So how about 1? I don't know. A3 could be whatever you want. A3 can be 100, 1, 5, pi, square root of 3. Doesn't matter. But let's just have A3 be 1. Now if A3 is 1, then A1 will also be 1, right? Because A1 needs to take on the same value as A3. And A2 will be the opposite of A3. A2 is going to be negative 1. And let's put those into the equation and see if it's true. All right, let's check this. And again, this isn't the only one. There's infinitely many. But A1 times V1. So 1 times V1 would be 1, 0, negative 2. Plus A2 is negative 1. So negative 1 times A2, which is 0, 2, 1. Plus, and then A3, we chose to be 1 times V3 is negative 1, the vector negative 1, 2, 3. Is this equal to the 0 vector? And it is, right? Let's take, real easy here. 1 plus 0 plus negative 1 is 0, yeah. 0 plus negative 2 plus 2 is 0. And then negative 2 plus negative 1 is, negative 3 plus 3 is 0. It works. So we have this relationship. We have v1 minus v2 plus v3 is equal to the 0 vector. Right. So these vectors, right, we have a non-trivial solution. So this set of vectors that we were given is a set of linearly dependent vectors, or I'll just say this set of vectors is dependent. All right. And as I mentioned, if you have a set of vectors that's dependent, that means you should be able to take at least one of these vectors and write it as some linear combination of some of the other vectors in that set. So if I took this here, pardon me. If I took this equation here and solve for, say, v1, get vector 1 alone. If I did that, then we would say, hey, look, v1, I would just simply add v2 and subtract v3. We got v1 is v2 minus v3. So you see, I can write vector 1 as a linear combination of vectors 2 and 3. So you could say that vector 1 depends on vectors 2 and 3, because it can be written as a linear combination of them. But I could also solve this equation here for v2, or we got v2 would be equal to v1 plus v3. Right, if I solve, just add v2 to both sides, you solve for v2. Again, we can see that one vector can be expressed as a linear combination of the others. I could have also solved this for v3. V3 would be equal to negative v1 plus v2, and you see that v3 depends on v1. Either way, no matter how I look at it, these are definitely dependent vectors, right? Not independent. If they were independent, I couldn't do this. You couldn't express one vector as a linear combination of any of the other vectors in the set. They're all separate and independent vectors. All right. So that was the first example. Now the second example is this set of vectors from R3, and let's take a look at those. All right, so we're given this set of 3 vectors, again from R3, right, 3 components. And again we're asked, are these particular vectors linearly independent or linearly dependent? All right. So to answer that question, again, you are looking at this equation. Some constant a1, some scalar a1 times vector w1 plus a2 times w2 plus a3 times w3. You take a look at a linear combination of the vectors and ask yourself, is there a non-trivial linear combination of these vectors that make the 0 vector? And again, this is the 3-component 0 vector, because all these vectors are from R3. So again, the trivial solution is always working here, right? If I replace, A1 and A2 and A3 with, all the number 0, this will work, right? So again, the big question is there any other solution, right, besides this? And again, if there isn't, then they're independent vectors. And if there is another solution, as we saw in the previous example, then they're dependent vectors, and I should be able to write one of the vectors as a linear combination of some others. All right, so let's just go straight to the system here, the augmented matrix for the system. So down the first column, I'll put vector W1, second column, vector W2, third column, vector W3, little bar for the equal signs, and then, again, the zero vector on the other side, or just zeros. It's a homogeneous system. Then I'll have the calculator do this, right? So let's have the calculator. I'll put this into reduced row echelon form, and I'll be right back with that. Okay, so again, I didn't enter the column of zeros. I just entered the coefficient matrix, the 3 by 3, because that column of zeros will not change. And then there it is in reduced echelon form. This left side is like, the 3 by 3 identity matrix. And you see how every single column of the coefficient matrix is a pivot column. Right? There are no free variables this time. So remember what that means. That means that there's only the one solution. Right? The only solution is that trivial solution. Is A1, first row says A1 equals 0. Second row says A2 equals 0. Third row says A3 equals 0. And again, so only the trivial solution works. So that means that this set of vectors is linearly independent, or just write independent, and that would also be fine. But this is a set of linearly independent vectors. Very good. And again, that means that you can't, none of them, you can't take any of these and write them as a linear combination of the other two, like I could in the previous example when they were dependent vectors. Okay, so again, very simple setup actually to check if a set of vectors is independent or dependent. Just take your coefficient, just make a matrix with those vectors as columns, put it into reduced row echelon form, and if every single column is a pivot column, then they're independent. And if there's a column that's not a pivot column, then they're going to be dependent, because there will be more than just the trivial solution to that homogeneous system. So very simple to tell. All right. So again, they go through that here. Talk about dependence, independence, all that. Now, it's even easier. We just saw a couple examples with a set of 3 vectors. And we'll look at sets of 3 vectors, 4 vectors, 5 vectors, whatever. It's even easier when there's only 2 of them. A set of 2 non-zero vectors is linearly dependent, if and only if one vector is a multiple of the other, meaning one vector is a linear combination of the other. Right? Because if there's only a single vector other than the one you're looking at, a linear combination is a scalar multiple. Also, I'm hoping this is obvious as well. If the 0 vector is in a set, then that set is linearly dependent. Right? Because you could multiply the 0 vector by something other than 0, and you're still going to get the 0 vector, right? So there's definitely going to be more than just that trivial solution. If you take a linear combination and set it equal to the 0 vector. And one more thing too. I talked about the pivot columns. If you take your vectors, make those the columns of a matrix, and then put that in echelon form or reduced echelon form. Remember, if every single column is a pivot column, then the vectors are independent. But if there's a column that's not a pivot column, then they're dependent. Well, that kind of leads us to this. if the number of vectors in the set is greater than the number of components in each vector, then the set is going to be linearly dependent, right? And that's because you set up that matrix. Say you have 4 vectors with 3 components. Then you'll have a 3 by 4 coefficient matrix. Put that in echelon form or reduced echelon form. You can only have at most 3 pivot columns. So at least one of those columns has to be a non-pivot column. So they're going to be dependent. Right, we'll see examples of that here. So using all these statements here, these 3 statements, they're asking us to determine. You can determine very quickly whether or not the set of vectors is independent or dependent. So if you have a set of just 2 vectors, say a set of 2 non-zero vectors is linearly dependent if and only if one vector is a multiple of the other, a scalar multiple of the other. Well, isn't this second vector 4, 8 just 2 times the first vector? So these are, or you could say the first vector is half the second vector, but they are scalar multiples of one another, and there's only 2 of them. So these are definitely dependent. Right? I can write one as a scalar multiple or a linear combination of the other. Now this one has 2 vectors. Now there's only 2 of them, and if there are only 2 vectors, it's a really easy check, to see if they're independent or dependent. Is negative 5, 8 a scalar multiple of 1, 0, or vice versa? No, because to get 1 to be 5, I'd have to multiply by 5. And if I multiply the second vector by 5, I get the vector 5, 0, not 5, negative 8. So these are not scalar multiples of one another, so they are independent. Again, this is only for sets with 2 vectors. Only for sets with 2 vectors is it this quick. All right, and then this third part ties into this statement here, right? If the number of vectors in the set is greater than the number of components in each vector, then the set will be linearly dependent for certain. Because again, you'll have at least one column that's not a pivot column when you put your matrix into echelon form or reduced echelon form. So that's what they're kind of getting at here. You see how there are 4 vectors in this set, but there are only 3 components in each vector. So when you set up your coefficient matrix, it would be a 3 by 4. And when you put that in echelon form or reduced echelon form, at least one of those columns is going to be non-pivot. It's not going to have a pivot in it. So these are going to be dependent. And you can tell that right away. Very easy check, because again, there are more vectors than there are components of the vectors. So these are linearly dependent. And finally, this one ties into that second statement. If the 0 vector is in the set, then they're definitely dependent. Right? This set of vectors here has the 0 vector in it. So yeah, I mean, the trivial solution would work. I could multiply all these by 0 and get the 0 vector. But, there's infinitely many other solutions, right? There are solutions to that equation that aren't trivial. I could multiply the first 3 by 0, and then I can multiply this last vector by anything I wanted. I can multiply the first 3 vectors by 0, and then the last vector by 5, and still have them add up to be the 0 vector. So you always have more than just the trivial solution if one of your vectors is the 0 vector. So these are also dependent, right? If the 0 vector is part of the set, that set of vectors is dependent. All right, then you have your challenge activity, which is the same question every time pretty much. So I'll start this and show you. So I have a set of these 3 vectors, and I'm asked, well, first they're saying make the augmented matrix. They already did that here. See, the first column is the first vector, the second column is the second vector, the third column is the third vector, and complete the reduced echelon form of the augmented matrix. All right. So I'm telling you right now, you could do, if I did -2 times the first row added to the second row, that would zero out this first row, second column, first row, first column, second row, first column entry, sorry. And if I take the opposite of the first row and add it to the third row, that'll zero out the third row, first column entry. So I get one with zeros. There's a pivot in each column. So when you put it in reduced row echelon form, you'll have the identity matrix on the left side, as your coefficient matrix will transform to the identity matrix. And if that's the case, if all 3 columns are pivot columns, then the vectors are independent. All right, and then check that. Okay, great. And again, you can punch this in your calculator. Just do it on the calculator like I was doing earlier. And again, they're independent, meaning that, none of these vectors can be written as a linear combination or a scalar multiple of the other vectors. All right, and then there are 4 of these levels. Now, I don't know if they're all the same like this. Let's see what the second one looks like. All right, a set with one vector, as long as it's not the 0 vector, right? A set with one non-zero vector is independent. Now, I know you can't see my choices, but here, linearly independent. If you, a single, because if I set, if I take a1 times v1 here and set it equal to the 0 vector, the only one that's going to work is a1 equals 0. The only solution to that equation would be the trivial solution. So these are independent. A set with one vector is definitely independent, unless it's the 0 vector, right? If it was just the 0 vector, it'd be dependent. Remember, any set with a 0 vector in it is dependent. Let me take a look at this last level. I'm not going to do it, but so the last level just says which of the following sets is always dependent. So a set of 5 vectors where each vector has 3 components. Yes. A set of 2 vectors where the equation has at least one solution. Well, this isn't always dependent. Right? What if the only solution is the trivial solution? And this set where this is true, right? This is a non-trivial solution to that equation. So these are dependent. So this is dependent. All right, I'll just do it. This one and this one. Second one, the set of 2 vectors where this has at least one solution. That one solution could be the trivial solution. All right, so there. All right. Now we're tying into a concept that we saw in the first section 5.2. All right, the linear independence and that concept of span. Now, if you recall from 5.2, the span of a set of vectors was the set of all linear combinations of those vectors. Now, what we're going to see here is that if a set of vectors is linearly dependent, that means I can write one of them as a linear combination of some of the other ones. So when I look at the span of those vectors, when I look at all linear combinations of those vectors, the one that can be written as a linear combination of others, I don't need it anymore. We can remove it and get a smaller spanning set. And we'll keep doing this until we get what's called a minimal spanning set. All right, so let's take a look at some of these statements here. Now, I've already told you this multiple times now. A set of vectors from Rm is linearly dependent if and only if, at least one of the vectors in the set is a linear combination of the others. You've already seen me talk about this. And then this concept of, like I said, minimal spanning set. The dependence relationship between vectors can be used to reduce any set to a minimal spanning set. So a set S that spans a subspace W, remember what that means. That means every vector in W can be written as a linear combination of the vectors in S. Hopefully you remember all that from section 5.2. A set S that spans a subspace W is a minimal spanning set if no smaller subset of S also spans W. Right, so meaning you can't remove any vectors from S. It's the smallest set there is that spans W. Alright, so the main idea is that if a set is linearly dependent, then vectors that are linear combinations of other vectors in the set can be removed without changing the span. This process can be performed iteratively until the remaining vectors are linearly independent, meaning take out one vector at a time until you have a set of vectors that's linearly independent. The remaining set of vectors from a minimal spanning set or form a minimal spanning set. Alright, in the animation below, the linearly dependent set v1, v2, v3 is reduced to a minimal spanning set v1, v2. So let's take a look. So here we have, consider the set of coplanar vectors. So we have 1, 0, 0, 0, 1, 0, and v3 is just a, see how v3 is just 1, 1, 0. v3 is just a combination of v1 and v2. So since v3 is a linear combination of these vectors v1 and v2, v3 can be removed from the set. Right? It's not needed. If it depends on these two, that means all I need are these two. Right? I can always make the third one if I want. So removing v3 does not change the span. Right? So the span of vectors v1, v2, and v3 is the same set as the span of just v1 and v2. Right? Because remember what the span is. Right? The span of a set of vectors is all linear combinations of those vectors. Well, if I have all linear combinations of v1, v2, and v3, and v3 is just a linear combination of v1 and v2, then I don't need v3. Right? So all the linear combinations of v1, v2, and v3 are just linear combinations of v1 and v2. So that's why they're saying the span of v1, v2, v3 is equal to the span of the vectors v1 and v2. And this is what we're going to be doing. Taking a set of dependent vectors and removing vectors until we have a set of independent vectors to form our span. And they talk about that here. Now, an easy way to do it, and I've been showing you, is to look at the echelon form or reduced echelon form of that coefficient matrix made by the vectors. So here's a very quick way to figure out what's a minimal spanning set. So suppose A is the matrix formed by the set of vectors v1 through vn as columns. Then a minimal spanning set, a minimal, not the, right? These won't be unique, but it'll be an easy way to find one. Then a minimal spanning set for the subspace spanned by U is given by the pivot columns of A. Right? When you put A into echelon form or reduced echelon form, the columns that correspond to the pivot columns from A will form a minimal spanning set for the subspace spanned by U. And I'll show you what I mean here. All right. So I'll write this out. We have vector v1 is 174, v2 is 3, negative 1, 2, v3 is negative 5, 0, 1, and v4 is 19, 10, negative 1. They're asking us to find a minimal spanning set for the subspace spanned by this set of vectors. Alright, so I'm going to go to a piece of paper and do this. Right. So here I am, there's that set of 4 vectors from R3. 3 components each that they gave me, and we know from again section 5.2 that the span of any set of vectors is going to be a subspace of the larger vector space that they come from. So the span of these 4 vectors, right? Remember, this is the set of all linear combinations of these 4, right? Some number times v1 plus some number times v2 plus some number times v3 plus some number times v4. All those. And it's the span of any set of vectors. This is a subspace of R3. It's a vector space on its own. Okay. But these vectors, v1 through v4, are dependent. this is a dependent set, and again, you can tell right away, you can tell very quickly because of that statement made earlier, right? See how there are more vectors than there are components. Right? There are 4 vectors, but only 3 components in each vector. So without even putting a matrix on paper, without even putting a matrix into echelon form or reduced echelon form, I can tell you right now that these vectors are dependent. So now the question is, which ones don't I need? So again, very easy. I can take this matrix here. So what we're going to do is we're going to reduce this set to a set of independent vectors. So I make a matrix with these 4 vectors as columns. 1, 7, 4 for the first column, 3, negative 1, 2 for the second column, negative 5, 0, 1, and 19, 10, negative 1. And again, there'd be like the zeros on the other side if I was checking for independence or dependence and whatnot. But all I care about is this coefficient matrix, though. Right? So I take this coefficient matrix and put it into reduced echelon. I like reduced. You can just do echelon form as well, because all you're looking for here are pivot columns. So again, I'll put this. Now this is a 3 by 4 matrix, this coefficient matrix. So I'm going to put this 3 by 4 matrix in my calculator and come back with reduced echelon form. So I'm back and put this 3 by 4 matrix into reduced echelon form. We have 1, 0, 0, first column, 0, 1, 0, second column, 0, 0, 1, third column. And then that's 1 and 2. You could change it, hit math, change the fraction if you want. That's 9 sevenths, 1 and 2 sevenths. And then negative 1, and then negative 4 and 1 seventh, so negative 29 sevenths. Right. But still, and then again you'd have the zeros on the other side, it doesn't matter. But do you see how there's the first column is a pivot column, the second column is a pivot column, and the third column is a pivot column, right? These first 3 columns are pivot columns. So their corresponding vectors, back in the original matrix, will be independent. And so vector v1, vector v2 corresponding to the second column, and vector v3. And we could easily write, if you wanted to find solutions to this equation here where I set, the linear combination equal to the 0 vector, you could, there's a free variable, and you can find solutions that are not trivial, and then solve for v4. All this is saying to me is that I can write v4 as a linear combination of the first 3. But we wouldn't be able to write v3 as a linear combination of the first 2, or these first 3 vectors, right, because they're corresponding to pivot columns. These first 3 vectors would be independent. Right. Now, if I changed the order, it would have changed, what 3 vectors I'm looking at. But still, I've got 3 of these vectors are independent. All right. So on the next page, we write that out. Right. So looking at the pivot columns and their corresponding vectors. So vectors, v1, the 1, 7, 4, v2, the 3, negative 1, 2, and v3, negative 5, 0, 1. This set of vectors is independent and spans the same set that the first 4 vectors do. And the span of this set of vectors is exactly the same as the span of those first 4. again, v4 here, I can write v4 as a linear combination of the first three. So we remove it. I don't need it, and just say all the linear combinations of these four are just linear combinations of these three. And then this would also be called a minimal spanning set. All right, so then this set here, this set with those three vectors, a 1, 7, 4, 3, negative 1, 2, and negative 5, 0, 1, is a minimal spanning set for this subspace. Because I can't remove any more vectors. Every vector in here is a linear combination of these three. If I were to pull one of these away, then there'd be some vectors in here that I couldn't get. Right? This is as small a set as I can have, so that every vector in here is a linear combination of them, and they're independent. Right. Okay. Easy enough, right? Very easy. Just putting it in, setting up a matrix, echelon form, reduced echelon form. Look at your pivot columns, and the pivot columns correspond to the vectors that will form an independent set. Now remember I said it forms a independent set. If I change the order, if I put these columns in a different order, I might have got different vectors. I might have had the vector 19, 10, negative 1 instead of negative 5, 0 if I just switched those. So it says here, see, however, this set is not unique because v2, v3, v4 would also be independent. And if you change the order. But let's just stick to the order they gave it to us and make it easy on ourselves. All right. So again, you have this activity here. So here v1 is 4, 2, v2 is 0, 5. These are independent. Remember, if there's only two vectors, they're going to be independent if they're not scalar multiples of one another, and these are not scalar multiples. So these are independent. So the span of these two vectors, you can't remove any of them, right? If I say and get the same span because they're independent. All right, so they're saying the span of v1, v2 is equal to the span of v1. No, because again, v1 and v2 are independent. So if I take one of them away, I'm getting a totally different span. So this is false. Now this set of vectors, right? These two vectors are dependent. Right? Again, when there's only two vectors, they're dependent if they're scalar multiples of one another. And this, if I multiply the first vector by 2, I'll get the second vector. So these are dependent, meaning I don't need one of them. And I just showed you, v2 is just 2 times v1. So I can write v2 as a scalar multiple of v1. v2 depends on v1. I don't need v2. All right, so the span of v1 and v2, all the linear combinations of these, is equal to the span of v1? Yes. You can absolutely remove one of these and be fine. And a set with one vector that's not 0, that's not the 0 vector, is independent. So we'd have a minimal spanning set there of just v1. All right. Now this one here, you'd actually have to go through and do, set up a matrix. So I'll do this one. So let's do. I'll show you the whole calculator process again. So I'd be setting up a 3 by 3 matrix there. Second matrix, over to edit. And it's a 3 by 3 with these three vectors, and we have 1, 4, 3 across the top row. Second components are negative 2, 0, and negative 1. Third components are 0, 8, and 5. Yeah, if there are more than two vectors, you're going to have to set up your matrix and put it in echelon form, reduced echelon form and stuff. Now my previous entry was reduced row echelon form, so here we go. And the answer is yes. Right? They ask, they say the span of these three vectors is equal to the span of the first two. Well, if you look at my calculator, Right, you see how only the first two columns are pivot columns, so those first two vectors, negative 1, 2, 0 and 4, 0, 8, those are independent. And you don't need this third one, right? Because you see the third column is not a pivot column, meaning you could write the third vector, you could write 3, negative 1, 5 as a linear combination of the first two, right, somehow. So you don't need v3. So the span of these three vectors will be equal to the span of these two. Right, so this is true. And again, you'd have to set up another matrix here. Now this would be a 4 by 3. Now let me show you. I'm going to show you this one because there's a tricky part to that. You can do it by hand. This would be a 4-row, 3-column matrix, right? 4 rows, 3 columns. There's only 3 vectors. Now let me show you what happens when you put in a 4 by 3 and try to put it in echelon form or reduced echelon form in the calculator. It comes back with an error for some reason. When there are more rows than columns, you get an error. I'll show you how to fix that if I haven't already in a previous video. But 4 by 3, all the first components are 1, 0, and 2. All the second components are 2, 1, and 0. Third components are all 1. And the fourth components are 4, 1, and 7. Now let me show you that when you go to put this in reduced row echelon form, it's going to come back with an error. And it says invalid dimensions. So I have a very easy fix for that. Alright, for some reason, again, I don't know why, but for some reason on the calculators, it doesn't put a matrix with more rows than columns in echelon form or reduced echelon form. So just add columns of zeros until the number of rows isn't greater than the number of columns. So that's a very easy fix. So let me show you. So I go back to this matrix here, over to edit. Now keep this the way it is. Just make it a 4 by 4, right, so that way the number of rows is not greater than the number of columns. And then in that last column, just keep it as a column of zeros. Remember, a column of zeros won't change, so just ignore it. Just keep those columns of zeros and ignore it, and now you can get it. See, so you see every column. Again, ignore this last column. Ignore the column of zeros. All 3 of the columns I care about are pivot columns. So these are independent. All 3 of these vectors are independent. So I couldn't remove any of them. Right, if I take one of them away, I'll get a totally different span. So the span of v1, v2, v3 is equal to the span of v1 and v2? No way. Right. Again, because these vectors are independent. So again, very quick fix. Just add columns of zeros to make sure that the number of rows isn't greater than the number of columns. Put it in reduced echelon form, and then just ignore those columns of zeros. And that's it for this. So, you got your additional exercises. Some of these are on assignment 8, some are not. I would still recommend doing all of them. I'd still recommend doing all of them. Get more practice, more exposure to the material, get better at it. You can also view the solutions, to check your work and stuff. Again, I say this every video. Please do the problem first. Try to work it out on your own. Try to figure it out before you resort to looking at the solutions. Because if you're just copying solutions down, you're not going to learn anything. Right. Yeah, so that's it for this concept of linear independence, linear dependence. It's very easy to check, especially with your calculators. Right. Just make a matrix with those vectors as columns. Put it into echelon form or reduced row echelon form. And then, if all the columns are pivot columns, then the vectors are independent. And if there are any columns that are not pivot columns, then the vectors are dependent. And the vectors from the original set that correspond to a pivot column those vectors would form an independent set on their own. All right, wonderful. So hopefully this video helps you out when you're going through this on your own. If you have any questions, send them my way, let me know. And thank you very much for watching.